Hi, everybody. So first of all, what is math? This is section 5.1, but what does math stand for? Mental abuse to humans. Just want to make sure we're clear on that. So now let's move on. Section 5.1. So here's the story. I've always given you a function, and I ask you, what's the derivative of the function? What if I take the derivative and I get an answer, and we look at the answer and say, hey, that's the answer. Well, I wonder, what was the original function that I took the derivatized? Actually, the word is differentiated. But what was the original function that got me to this? It's kind of like forensic. It's like forensic math. You're looking at the dead body and you're trying to figure out how it got there. So what if, for example, let's scroll down a little bit. What if, for example, I had f prime. I told you that f prime of x is equal to 2x. And I want to know what was the original function f of x that when I took the derivative, I got an answer of 2x. Well, I think you guys are all smart, and you realize that the answer is x. Smarter than me because you know how to do. Okay, you realize the answer is x squared. You realize the answer is x squared. What if I had some function, I took the derivative of the function, and I got. Oh, why am I saying that? Because if I take the derivative of x squared, the answer is 2x. You guys realize that? Suppose I had a function, I took a derivative, and I got 3x squared. Ooh, 3x squared. Well, what was the original function? Well, you guys are very brilliant. So you realize that the original function was x to the third power. But some of you might be thinking, and by the way, I hope that this class causes you to do that, to think. Oops. And you may be thinking, wait a second. What if the original function was x squared plus 3? Oh. That's I didn't want that. I want it all in one line. Sorry about that. What if the original function was x squared plus 3? Wouldn't that also work? If I take the derivative of x squared plus 3, well, when I take the derivative of the x squared, I get the 2x. When I take the derivative of the 3, I wind up getting 0. It disappears, goes on vacation. So my answer is still going to be 2x. So x squared is kind of like my main answer, and the 3 is like sort of just something that doesn't matter, because it could be 3, it could be 13, it could be whatever you want. So what we're gonna do in general now, we're gonna use a notation, and the same thing with x to the third, same thing with any of these. So we're just gonna use a letter C, or any letter, it doesn't matter. Usually C stands for constant. So if the original function is x cubed plus any constant, it could be x cubed plus 17, x cubed minus pi, x cubed plus e to the third power. It could be x cubed plus, a million. Doesn't matter, because when I take the derivative, that constant, what's the constant? Just a plain number. That plain constant number is going to disappear. So that would be, so therefore I would still get the answer of 3x squared, no matter what that constant is. Now, suppose my answer is, let's continue. So everything here, I'm going to always add a plus C. Suppose my answer was 1 over x. What is the original function? Well, the original function, I'm sure you guys realize, is going to be ln x, and I'm just going to add the plus C. I think I'm just going to track this. I just want my answers to be. That's me. Anyway, how about e to the x? Well, that'll be e to the x plus c. There you go. What if, let me do another one now. What if f prime I'm gonna copy this template here. I'm gonna change it a little bit, but I'm gonna copy this. Suppose f prime. Let's give another example. Equals 1 over x squared. Oh, sorry, actually negative 1 over x squared. What would the original function be? What would be the original function? So the derivative is negative 1 over x squared. Anybody know what the answer would be? What function, if you differentiate it, do you get negative 1 over x squared? Now I'm going to teach you kind of rules for these things and formulas and all kinds of stuff. But now I just want you to know. Now I just want to see if anyone knows just from experience. The answer is going to be 1 over x, because the derivative of 1 over x, we learned that is negative 1 over x squared. I just want to kind of get your, whatever. Anyway, so that, my friend, is the one. I want to do one more. Suppose my function, the answer after differentiating, how do you do this square rooty thingy? Special 1 over the, well, that's big. 1 over the square root of x. The 1 over 2 square root of x. 1 over 2 square root of x. The original function, as you guys probably may remember, what is it? Anybody remember? It is, drumroll please, square root of x plus c. So the plus c is just kind of like I don't want to say a dummy variable, but actually let's look in the textbook now, and I want to show you something, a little insight about that, about the plus c and some other things. All right, so here we go. What about the so we're in section 5.1, antiderivatives and indefinite integrals. So I want to kind of now that they're giving this little introduction, I wanted to, before we get into all the, because the textbook has all the fancy ways of saying it, so I want to kind of say it just straight. I like saying in plain English, if you will, so to speak, and then we can look at all the then all the fancy stuff will make sense. See, when you look at a math book, it's all these complicated formulas, but they're not that complicated necessarily. It's just they have like ways of saying stuff, more formal ways of saying stuff, and if you don't know what they're talking about, you're like just totally lost. But really, the ideas that they're saying are pretty straightforward. Really, everything I explained to you already is pretty much all there is. We'll get with it, still more details, more theorems, more formalization, and so forth. But let's look at this. So the word we use for this, what we've been doing this whole time, is called the antiderivative, meaning I give you the function, and you have to figure out what was the original function which got differentiated to get the function that's presented to me. So we call that the antiderivative of a function. So if I am the derivative of you, you are the antiderivative of me, and vice versa. That's really what that means. So a function f, a function we're using the letter capital F just to distinguish, is the antiderivative of a function small f, and they're just using capital F and small f to just, I like that. I actually like that idea for the notation, because this way it shows that these two functions go together. So small f and capital F, small g, capital G, so I kind of like that I find it really convenient having a small and capital the same letters, so you know which function, which derivative goes to which antiderivative and so forth. Anyway, so capital F is an antiderivative if capital F prime equals plain f of x. So it's an antiderivative of f. So the function f of x is equal to x cubed over 3. That's an antiderivative of the function x squared. Interesting. Why is that? Because if I would take the derivative of x cubed over 3, the derivative of this is just plain x squared. Why is that? Because if I take the derivative of the top, I wind up getting 3. And the reason is, actually, let me just, I just want to show you this, why this is. Just show you this just show you why this is true. So the derivative of x cubed of x cubed well, we know with the derivative, you're allowed to take you could take the derivative out of the thingy thing, and I get 1/3 times the derivative of x cubed. But the derivative of x cubed, so this is going to be 1/3. The derivative of x cubed is the derivative of x cubed is 3x squared. We have that right up here. And let's not forget the plus c. Anyway, but this is equal to this is going to be equal to 1/3 times 3. 1/3 times 3 is just plain x squared. And that's where it comes from. Now, this idea is really going to work with any function and any power kind of function, and we'll see in a second. So in other words, the antiderivative of x squared is going to be x to the 3rd over 3. The antiderivative of 2x is x squared, which means the antiderivative of x is going to be x squared over 2. Well, I'll spell that out in a moment when we get to the we're going to see the formula for this. So let's see. Now, x squared is not the only antiderivative, because x cubed over 3, x cubed over 3 is not the only antiderivative, like I was saying, because if I add a 2 or I subtract pi or I add square root of 5, I still get the same answer. So really any constant, any real number c usually, c stands for constant, will be an answer, will be an antiderivative. So in other words, if I have a function has only one derivative, but a function has infinite amount of antiderivatives. Now, when I say infinite amount, it's really one thing, x cubed over 3, but there are infinite possible constants I could add onto it. So there's like sort of one primary answer and infinite of those constants. Okay, let's anyway, here's an official theorem. If the derivatives of two functions are equal, so two functions have the same derivative, then the functions differ by most a constant. So in other words, if I have two functions and their derivative of each function is x squared, then I know that the functions are x cubed over 3 plus 7 and x cubed over 3 minus 9, or something like that. But the x cubed over 3 part, that's like the solid part, and then what constant I add is what varies. That's really what theorem 1 is saying. I'm trying to put this all in play. Me personally, I love the technical language of mathematics. And the precise. You guys, I'm trying to make it just a little more just common sensey, and which is how I always learned it at first, sort of a common sense way. Once you know the common sense, then all the technical jargon, kind of makes fits in. Anyway. Now, the derivative of x squared over 2 is equal to x. because the derivative of the top x squared, now this is not a quotient rule thing really. It's I'm just going to take the derivative of x squared and multiply it by the constant 1/2, just similar to like what I did on the similar to what I did in the other one, in the x cubed over 3. Anyway, I'm just so a half times 2x gives me 1x. But what are the antiderivatives of x? What are all the antiderivatives of x? Well, x squared over 2 plus k. Now they're using k instead of c, doesn't it? But if you graph it, you wind up getting sort of a family of parabolas. See, because x squared over 2 is a parabola. So this is x squared over 2, that's x squared over 2 plus whatever, that's, I can't say it's 1, that's x squared over 2 plus 2, x squared over 2 plus 3, whatever, you know, or it could be x squared over 2 minus 5. So really, they call this we call this a family of functions. Oh, isn't that sweet? Family. It's a family of functions. The function family. Da, 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 da. That was an old TV show, The Addams Family. Family Guy. Function Family Guy. Anyway, but I digress. A family of functions. Now, really, if you look at every single possible antiderivative, you get all these parabolas which fill up, and if I take all of the parabolas, there's an infinite amount of them. If I would like take the union, sort of combine all these parabolas together, what I would get, it would fill up the entire plane. There's not one spot, there's not one point on the plane that wouldn't have a parabola going through it. That's number one. Number two, none of these parabolas would touch each other. None of them would intersect. Even if I make them extremely close to each other, like x squared plus 5 and x squared plus 5.00001. Even if they're extremely close, none of them will actually touch, but they'll fill up the entire plane. So that's a family. And that tends to happen with families of functions. But that's kind of what we're looking at here. Anyway, so now there's something we call an indefinite integral, and we use this symbol. It's kind of like a big. It's kind of like a stretched out S. And now I'm calling that a stretched out S for a reason, because the word we're going to learn eventually that the word S kind of stands for some SUM, not SOME, but SUM. Anyway, this is called an integral sign. So the integral, so we say the indefinite integral of f of x dx is capital F of x plus c. This is again when f prime, capital F prime equals small f. And again, all this is taking all the stuff that we said already, and now we're just using a different notation. So we haven't, nothing has happened. No math has actually taken place. We're just introducing a new notation. This big stretched out S is called the integral sign, and f of x, the function that goes inside the f of x is called the integrand. I don't know anyone who actually calls it that, but technically. But here's something we do. Here's a word that we do. Is like the constant c that I add on. We call it the constant of integration, because the only reason why, and that actually makes a lot of sense, because the only reason that plus c is there is because when I take the indefinite integral, which is the same thing, which is just another word for the antiderivative, I have my main answer, and I have to tack on that plus c. So the only reason that plus c is there is because of the fact that I did an active integration here. Alrighty, moving on. So let's get down to, okay. So now here's something we might have kind of like gotten a hint to. If I have the integral, now I'm going to say the integral of, I'm not going to keep on saying indefinite integral because it's just annoying. So I'm going to say the integral of x to the n, so like x squared, x to the third, x to the, is going to be x to the n plus 1 over n plus 1, and then tack on that constant. And this actually, we saw this because we saw that the integral of x to the first power is x to the squared over 2. We saw that the integral of x to the second power is x to the third over 3, which means, so this is really kind of a pattern that we started to see. Now, if I have, notice it says n does not equal -1, because if n was equal to -1, it would be 1, that would be x to the -1 power, which is 1 over x. And 1 over x, the integral of that we know is ln x. Notice they put the absolute value. The reason we put the absolute value is because ln is only, a logarithm is only defined for positive numbers. So we put the absolute value to make sure that inside the ln is a positive number. By the way, another reason. So 1/x is kind of the exception to this power. This sort of, it's a power rule in reverse. It's like reverse power rule. 1/x is kind of the exception to that, and it actually makes a lot of sense because if n equals -1, I have -1 plus 1, which is 0 on the bottom of a fraction. So it's all undefined. So it is kind of cool that when it's x to the -1 power, instead of getting another exponent, instead of getting another power function, I just get this ln thing, which is whoa. Now, how do we know all this? All this stuff can be proved. It's a whole thing. We're not going to, in this class, we're not going to go through all. In this class, we're going to go through more the applicable and functional aspects, of the calculus, and we're going to learn the basics. I'm not just going to throw a bunch of formulas at you. I'm not just going to throw. I'm going to explain what everything means, and I'll show you a little bit where things come from, but it won't be an intense, proving everything the way I would if this was a calculus class just did that. Some calculus classes will do that. This is for Miramar College, right? So in Miramar speak, if you take Math 150, so that's a calculus class where it does go more into depth of proofs and things like that. This class, Math 121, is more of we give you the basics of calculus, and actually, I should have said this all on day one. I don't know why I waited till chapter 5 to say all this. We give you the basics of give you the basics of the calculus and explain what it all means, and then show you how to use it to, for different applications, business or science or whatever. Anyway, the integral of e to the x is e to the x plus c, and we saw that also, one of those practice, at the beginning of this video, we saw that the antiderivative of e to the x is just e to the x, and then you just throw in the plus c. Okay, so that's cool. And now, indefinite integrals. So here's some more properties of indefinite integrals. If I have the integral of a constant times a function, that's going to be equal to the constant times the integral of the function itself. And I kind of did that when I pulled out the 1/3 and I pulled out the 1/2. That's kind of what I did. We were calling it antiderivatives then, but that's kind of what I did. The integral of a sum is equal to the sum of the integrals. The integral of a difference is equal to the difference of the integrals. Now, by the way, this comes from, this is true. This number 5, that's true for the limit. The limit of the sum is equal to the sum of the limits. That's true for derivatives. The derivative of a sum is equal to the sum of the derivatives. And it's true for integrals that the integral of a sum is equal to the sum, SUM, of the integrals. And that makes sense because integrals conceptually come from derivatives, and derivatives conceptually, kind of come from limits. And we've kind of explained that throughout the course. The indefinite integral of a constant times a function is the constant times the indefinite integral of the function. Okay, that's lovely. So let's carry on. Caution. What's the caution? I feel so caution now. Oh, so this idea of pulling a number out of the integral, I can pull a constant out of the integral. So 5 times the function is equal. The integral of 5 times the function is equal to 5 times the integral of that same function. But I cannot pull an x out. I can't say that I have x times x to the half. That's pull the x out and now have the x to the half inside, because I can only pull a constant out of a function. I cannot pull a variable out of the function, out of the integral. So just be cautioned about that. I hope you're all scared and quivering and shaking your boots right now. Anyways, if I have the integral of e to the x plus 1/x, well, it's going to be, I'm going to take basically what we just said is that I could just take each one individually. So the integral of e to the x is e to the x. The integral of 1/x is ln x. And I always throw in the plus c. I don't have to throw in 2 plus c's, because the plus, like here it says plus c1 plus c2, constant 1, constant 2. But they kind of like mush into one. What's the difference? So if I have the first constant is 3 and the second constant is 4. Why don't you just say, I'm throwing in a 7? So we don't bother writing C1, C2. We just write C constant. But in theory, there really were 2 constants, but they kind of got mushed together into one. We say they get absorbed together. Gets absorbed into the constant. So sometimes you'll have something where it says e to the x plus 17 plus c, so I get rid of the plus 17 because the 17 kind of gets absorbed into the constant. That's a way, it happens sometimes. Anyway, the integral of 5 is just 5x plus c. The integral of 9 e to the x, that's 9 times the integral of e to the x, which is 9 e to the x plus c. These are all the integral of 5 t to the 7. I pull out the 5. The integral of t to the 7 is t to the 8th divided by 8. These are all the rules that we've seen. And now my final answer is just 5/8 t to the 8th plus c. And these are basically power rule. This is the e to the x rule. These are the power rules, and it's all good. All right. The integral of 4x cubed plus 2x minus 1. So again, I do all 3 to 7. Now, if it was a derivative, the minus 1 would disappear, but it's not a derivative, it's an antiderivative. So I do each one separately. The antiderivative, or the integral of 4x to the 3rd, is 4x to the 4th over 4. Of course, these 4s are going to cancel, so just have plain x to the 4th. The integral of 2x is going to be 2x squared over 2, which then just becomes x squared. The integral of minus 1, it becomes minus x, which is already in lowest form. And of course, let us never forget the plus c. Notice they put the plus c up here, they didn't just put it in the bottom, because once I get rid of these integral signs, then I'm ready for the plus c. So as soon as the integral signs go, as soon as we integrate, that's when we put in the plus c. I want to make sure that I did it that way on my, let's see, did I not? Really, I should have put the plus c over there. I just was kind of being lazy here and didn't put a plus c, but I want to show the proper. I do want to show the proper form. So so the derivative, so d dx of x cubed over 3 is 1/3 d dx of x cubed. Oh, actually, you know what? I take it back. This didn't have a plus c. Oh boy, I just made a fool of myself. Sorry. Okay. Anyway, that's right. Now I remember. That's why I didn't do it. Anyway, that's awkward. So let's find the indefinite integral. So the integral of 2. Oh, match problem. We're not doing the match problems. Okay, example 3. Using the indefinite integral properties and formulas. So here, 4 over x to the 3rd, that's 4 times x to the negative 3. So the integral of x to the negative 3 is x to the negative 3 plus 1 over negative 3 plus 1, which comes out to x to the negative 2 divided by 2, but the divided by 2, or negative 2, I should say, cancels out with, partially cancels with the 4, and I get negative 2, x to the negative 2 plus c. Now, the cube root of x of u squared. By the way, you always have the dx and the du, or whatever the variable is, you have the d, whatever that thing is. That's always the form. And when you write an integral, you always put that in that dx or du or g, whatever the variable is. So this I'm going to rewrite as u to the 2/3. So the power goes on top, the root goes on the bottom. So u to the 2/3. Now I'm going to use that power rule. The 5 is just sitting there, so it's 5 times u to the 2/3 plus 1 over 2/3 plus 1, which crunch, crunch, crunch becomes 3 u to the 5/3 plus c. Pretty awesome. This guy over here. Now for this one here, it's easier to split this into 2 fractions. So this fraction, when I split it and then reduce it, I get x minus 3x to the negative 2, which using the power rule gives me these guys here, and then just crunching that down gives me 1/2 x squared, 3x to the negative 1 plus c. And after a while, when you do enough of these, you get the hang of it. You get to a point where you just do it, like you just look at it and see what the answer is going to be. Which is why I'm so nice. It's so nice of me that I give you like a lot of homework so you could do these problems and and just get like second nature. I just, when I was in school, I was okay. I'm gonna be honest with you. I just loved math, and I didn't do this because I was a good student. I actually was never really a good student ever. But I loved math. I was like obsessed with it. So when we had homework, what I would do is that, let's say, for example, let's say the teacher would give us do all the odd problems. So not only would I do all the odd problems, I would also do all the even problems, because I just wanted to solve every single problem that there was. And then after I did everything, did all the odds and all the evens, then I would do them again. I would like just go on a new piece of paper, not look at any of the work I did, start from scratch, just do everything from scratch. And I would do it a third time, and sometimes a fourth, because I wanted to get it down, like, so it was like a reflex. I wanted to get it down, and it was just, I just knew it instantly. Why? I don't know. I just did. I literally don't know why, because I was never, no teacher told me how to do that. That's how I was. That's just what I wanted. That's how So that was my story. And then when I finished all that, I would make up problems. Oh, what if it was this? What if it was x to the fifth? What if it was x to the ninth? What if it was divided by, what if it was 17.4? I would just make up variations of the problems. Why? I just, I don't know, you're just obsessed with something. It's like if you're really into, basketball, you're going to take every shot, you're going to keep on practicing. You hear about these basketball players who would stand there on their own time, on the free time, they would take 100 free throws and just keep on getting it, and then they would try to work out these little new wiggly moves or things. That's just, I can't explain it. When you're into something, you just want to do it. That's the story. Okay, now here I'm going to write this as a negative, as exponent. So this is 2 times x to the negative third minus 6 times x to the 1/2. Which once you have it written that way, now I just follow the process. It's a lot of fractions, crunch. But I'm ultimately going to get 3x to the 2/3 minus 4x to the 3/2 plus c. And this guy here, now for this one here, it's much easier to just distribute the x into the parenthesis. Now I have two different power functions. So I have x to the 3rd, which integrates to x to the 4th over 4. I have 2x, which integrates into x squared. And then, of course, I just put on the plus c. So once the integral goes off, that's when the plus c comes on. That is the story. Ocean. Ocean here. Very cautious. The indefinite integral of the quotient is not the quotient of the indefinite integrals. Okay, that's true. That's true. A lot of these things, I don't know who would ever think this. I don't know who would ever think this, but you never know. People might, you never know who's going to think what. Okay, let's look at an application here. So we have a particular, so find the equation of the curve that passes through the point 2, 5 if the slope of the curve is given by dy dx equals 2x. Now, if they're saying the slope of the curve is given by dy dx equals 2x, that's a fancy way of saying that y is the antiderivative of 2x. Because when I take a derivative, that gives me the slope of the tangent. So if the slope of the tangent is 2x, that means the derivative is 2x, which means my original function is going to be the antiderivative. This is a very sneaky way of just saying, hey, give me the antiderivative. So dy dx equals 2x, and now when y equals 5x equals 2, we're going to save that. We're going to save this. That's important information. We're going to save it for the end. So first, we're going to say y equals the integral 2x. Therefore, y is equal to x squared plus c. Now, what we want to do, we want to find the exact particular equation that gives it. We don't just want a plus c, because plus c could be any one of an infinite amount of equations. There's one equation that's going to work here, and it's the one that goes through 2, 5. So I'm going to use the point 2, 5 to plug it in and then find the value of c. Because if y equals x squared plus c, that means 5 equals 2 squared plus c, because I'm taking it from that point right there, 2, 5. And now that tells me that c is going to be equal to 1, because 5 is equal to 4 plus c, so c equals 1. So my function now is y equals x squared plus 1, which looks like that guy right there. So this one right there So I remember I said all of these parabolas, they cover the entire, they basically wind up covering the entire plane. If I look at all these infinite parabolas, I can't draw infinite parabolas, but they wind up covering the entire plane, and none of them touch each other. So there's only one of them that's going to go through the point 2, 5, and that's the one we're looking for right there. So this is awesome. All right, well, that was, okay, cost function. If the marginal cost function of producing X units of a commodity is given by C prime equals 0.3x squared plus 2x, and the fixed cost is 2,000, find the cost function C of X and the cost of producing 20 units. Okay, so that's the marginal cost, and the fixed cost is 2,000. Now, when they say the fixed cost of 2,000 is 2,000, that's another way of saying that the constant in that function is going to be 2,000. Because whenever you have C of X is equal to some function of X, if the fixed cost is 2,000, that means C of X, the cost function, is going to be some function, something of X, X squared, X cubed, square root, whatever it is, and then plus 2,000. That's because the fixed cost is going to be there even if X equals 0 and everything disappears. Anyway, but let's see let me see what we're talking about. So we know that C prime of X is equal to 3.3x squared plus 2x. We know that if I stick 0 and I get 2,000, so I was just explaining to you, because even if you do absolutely nothing, it costs you $2,000. That's what fixed cost is. In other words, I have to rent the factory, whether I make 1 bicycle or make 1,000 bicycles. I have to pay the same rent on the factory, or something like that. If I have to turn the lights on, I'm lighting up the whole factory, whether I make 20 bicycles or 500 bicycles. That's fixed cost. Or I have to pay the janitor, whether no matter how much I'm making. Fixed cost means it's things which have nothing to do with how many products I produce. Anyway, C of 0, or how many miles a drive or whatever. Like you rent a car, so you can say it's $50 a day plus 10 cents a mile that you drive. So that $50, even whether you drive 1,000 miles or whether you just park the car and don't drive it at all, that's going to be that $50 is going to be the same $50. That's what a fixed cost is. Anyway, so this is my C prime. C is going to be the integral. We know from crunching that's going to be 0.1x to the third plus x squared. All the steps are right here. We've done this a million times already. And now plus k, but k is just going to be 2,000. We said it right here. So this is my final thing. Cost of x. C of x is going to be 0.1x to the third plus x squared plus 2,000. And now, what's the cost of 20 units? We'll just plug 20 in for x, and I wind up getting crunch, and I wind up getting $3,200. And that is the story. A satellite radio station launched an aggressive advertising campaign 16 days ago in order to increase the number of daily listeners. The station currently has 27,000 daily listeners, and management expects the number of daily listeners, S of t, to grow at a rate of S prime is equal to 60 t to the 1/2 power listeners per day. So if you're a new listener, they're going to square root you and multiply it times 60. And that was a joke. Anyway, so how much longer should the campaign last? The station wants the number to grow to 41,000. So first thing we're going to do is find S of t. We know S prime, and we know that S of 16 is equal to 27,000. That's what we just said. That's 16 days ago. I'm sorry, not 16 days ago. We started 16 days ago. Now it's day 16, and we have 27,000. So that means S of day 16 is 27,000. So S of t is equal to the integral of 60 t to the 1/2 power dt. And now this is just a crunch, and I get 40 t to the 3/2 power plus c, and which is awesome. And now all I got to do is start plugging in order to. Now I just got to find the c, and to do that, I'm just gonna plug in t equals 16, and over S of t is going to be 27,000. And we wind up getting, again, this is all stuff you just crunch out in a calculator. So C is going to be 27,000 minus 40 times 16 to the 3/2 power, which again, crunch it out on a calculator, you get 24,440. That's what the constant is. By the way, this a little confusing here because the C here does not stand for, in the previous problem, C stood for cost. C of x. Here that we're using the c as the constant of integration. Anyway, so s of t, so we have here, so we solve s of t equal, so now I want to know what day, when t stands for time, or in this case, it's time in terms of days. So how many days, how many days is it going to take before my function winds up, the value of it winds up being 41,000, meaning the number of listeners is 41,000. So I just take the function, I just take the s function, which is 40 times t to the 3 halves plus 24,440, which is what I figured out a minute ago. Set that equal to 41,000. Crunch, crunch, crunch. Again, you can do also the calculator, and you get 55.5. So it's going to take roughly, and we already on day 16, so it's going to take roughly 40 more days to reach our goal. Hopefully, that's assuming all our market analysis is correct in the first place. But we're mathematicians. That's so. In a business, different people do different jobs. Someone came up with this idea that this formula is going to work, and now I'm taking it and crunching it to use the formula. So everyone has their own jobs of what they do in a company. Anyway, and that's the way it is in life. The baker does one job, the farmer does a different job. The machinist does a different job. Everyone does their jobs, and everyone helps everyone else. Anyway, it's been absolutely delightful. This is the end of section 5.1. We'll continue next time. And till then, I'm saying bye.